Alright, so in this video, we are going to understand the spectral, temporal, graph, neural network for multivariate time series forecasting. Okay, that's a lot of words. And my goal today by the end of this video is to make sure you understand what each and every word means, what each and every word's purpose is, and how all of these words come together to facilitate all of these words. So let's talk a little bit about the paper first. So this was a paper, Spectral Temporal Graph Neural Network for Multivariate Time Series Forecasting. This was published by Microsoft and it was published in NIPS 2020. So in this paper, they're going to use graphs. They're going to use some graph thing. They're going to use some spectral temporal thing. And then we're going to obtain multivariate time series forecasting. Okay, so let's go from here. So I am assuming that you know a little bit about machine learning, a little bit about deep learning, a little bit about transformer architecture, and a little bit about what graphs mean, what the data structure graph is. So this is my promise for the end of the hour. We're going to use the transformer attention mechanism as a way to generate correlation in data. Okay, that's the first line. I have no idea what it means, but we'll demystify it as we go along. We'll build intuition for spectral graph theory. Okay, so this seems important. We'll understand the Laplacian. We'll understand the graph Fourier transform. And from graph Fourier transform, we can also, it's only natural that I give you a refresher of how discrete Fourier transform works, on how Fourier transform usually works in time series in audio and signal processing. Then we'll understand the graph convolution in spectral domain. So I also want you to have a very vague idea of what convolution means, at least in the convolution neural network sense or convolution in signal processing sense. And then we'll go and discuss the StemGNN's results and what this paper is and what it did. So here's the intuition. Let's focus on only the top half of this page for now. We'll have an input. We'll make a graph out of that input. We'll learn things from the graph. And from those learned things, we're going to enjoy the outputs. So this is a 1, 2, 3, 4-step process. I mean, hardly one, but it's a 4-step process. So we'll have input n time series, multivariate time series. They're going to make a graph out of it. Okay, this seems very absurd. Like how are we going to make a graph out of n time series in one dimension? We'll see. Then we'll learn things from the graph. This is where the main contributions of the paper come, and then we'll enjoy outputs. So somehow turn multiple time series to graph. So the first natural idea is to represent each node of a graph uh, as a time series. Each and every time series is a node in the graph. Okay, fair enough. All of these time series have data points. They are, for example, not only in this layer of the paper, but they're also stacked on top of each other. For this is t equal to 0, and above this is t equal to 1, and so forth. So this is a graph where each and every node of a graph is a time series. So then how do we put edges? So how do we put an edge between 1 and 2 and 2 and 5 and 2 and 3 and not between 1 and 5? How do we decide that? So maybe put an edge to represent time series that are close to each other. Okay, that's a natural idea. For example, if time series 1 and time series 2 are very close to each other in some sense, in air quotes sense, then put an edge between 1 and 2. If 2 and 3 are close to each other, put an edge between 2 and 3. But if 1 and 5 are not close to each other, why bother putting an edge over there? So perhaps use something like a correlation of any two time series to represent this closeness. Okay, that's a good idea, but we would like to use some deep learning way to extract this correlation. So this is where I'm assuming you have a little bit of a knowledge between a little bit of knowledge of what attention mechanism is and how transformers work. But nevertheless, let's just look into it. So what attention mechanism is, for example, you have three inputs and you're trying to calculate how each and every input is correlated to each other, like what is input one's effect on input two, how input one is related to input two, and how input two is related to input three, how much attention input one is paying to input two, and input two is paying to input three. So what attention mechanism does is it generates a key and value pair of each and every input. This key and value pair are generated by some matrix that is learnable. And for each input, there is going to be a query vector. So if you can look at this rapidly moving image, there is this query thing on the left hand side here. And as you can see, this query arrow moves from input 1 in this case, input 2 in this case, and input 3 in the third case. Now, each and every query is multiplied with, is somehow calculated that how each and every input relates to query of each and every input. So first of all, we have inputs. We have each and every input's key and value pair. And then we send a query that relates to each and every input, and we try to calculate in some sense how this query is related to all three inputs. So for SQL and Pandas people, they know like if we send a query and it matches with the key, then we say, okay, it's a very high score. If we send a query and it has not that much score with the key, then we say, okay, it's not related to our search. So this is what's going on. Let's skim over the details and let's just assume that this attention mechanism generates outputs which represent how each and every input is related to each and every other input. So it generates let's say n by n matrix where each and every row and column gives me that how much this particular row is paying attention to this particular column. So we can use this. This seems like a good idea. We can use this to find that correlation between 2 points. And let's move on from here. So this is just a bit of a digression. The most important formula in deep learning after 2018, this was the attention mechanism formula. So if we have a look over here, we have an input sequence of n tokens of dimension d. So n, basically n inputs with dimension d. That's just, let's assume d equal to 1 for uh, example purposes. And we have a query vector, we have a key vector, and we have a value vector, right? So the query vector is generated by multiplying this our x with some weight q. Key vector is generated by multiplying with x with some weight k, and value vector is generated by multiplying with some weight w. And then the self-attention mechanism is just this formula. We take a q multiplied with q transpose, we divide it by dimensionality. This is for normalizing our stuff, dividing by the square root of dimensionality and then multiplying it by the value vector. And then in the end we'll get attentions between each and every node, so to speak. So first the input, in our case, n cross t time series. So n time series of t time lengths, right, is fed into a gated recurrent unit. So this is a RNN which calculates the hidden state representation of each timestamp t sequentially. So this is an RNN in which each and every one of our time series goes, and a hidden state is calculated again and again and again. Then we use the last hidden state R sorry, as a representation of the entire time series and calculate the weight matrix W by the self-attention mechanism as follows. So after a gated recurrent unit goes on for time t points, it learns something, and in the end, whatever is the last hidden state value, we're going to use that to calculate our attention mechanism between series. We're going to use that as our x in our attention thing. So, and then we're going to calculate the weight matrix, and this weight matrix we are going to use to generate our graph. So we have a q, we have a k, and we have a weight matrix that is qk transpose softmax of that of divided by square root of dimensionality. So it's a very similar formula as to what we saw over here. It's just that we're not multiplying by the value vector because we are not per se concerned with the attentions. We are only concerned with the weights, and because we are only interested in generating a graph out of this. So let where q and k denote the representation of query and key, which can be calculated by linear projections with learnable parameters wq and wk in the attention mechanism respectively, and d is the hidden dimension size of q and k. The output matrix W is going to be an n cross n matrix. It's served as the adjacency matrix of the graph G. The overall time complexity of self-attention is n squared d. So this entire slide is lifted directly from the paper, and they have done some time complexity analysis, and they conclude that it's going to be an n squared d. They go of n squared d type complexity. So even if you have not understood it, it's not a big deal. We can discuss attention detail in some other video, but let's just focus, let's just understand that via attention, we have generated a weight matrix and we are going to use that weight matrix to represent our graph. So we have completed till the latent correlation layer. We have a graph ready. Now we have to learn things from this graph. So let's deep dive into this particular block over here. We see that there is block 1 and a block 2. There are two StemGNN blocks. And what each StemGNN block does is it has a GFT, that's a graph Fourier transform. Then it has a spectral sequential cell in which each and every time series is manipulated in some way. Then we have a graph convolution. Then we have an inverse graph Fourier transform. And then we can forecast. So basically what is happening over here? Why is this being done? So when starting the paper, Microsoft had a very clear objective. For example, we have n time series like this. This is one time series, this is second time series, this is third time series, this is a fourth time series. What they want to do is somehow they want to learn how this time series is related with each and every other time series, and also to understand what is going on in this particular time series as well. So basically a time series, what its particular characteristics are for a particular time series, and how these characteristics are dependent, how this characteristic play as a big whole in n time series. So I apologize if I'm not being articulate, but what they want to do is analyze each time series as it's on its own, but also as a part it plays in this big n time series thing. So it makes sense because each and every time series is an individual on its own, but it also has a part to play in the n dimensional, in the n time series overall. For example, let's take an example. If we have stock market time series for the stock of Microsoft, and it goes up and down like this in some sense. But we have n Nasdaq stocks which have Tesla and Google and Amazon. So we want to understand how Microsoft stocks behave, but also how Microsoft stocks behavior affects Tesla's stock, affects Google's stock, affects Amazon's stock. So this could be a very crude example, but this is what's going on over here. So why did I say all of these words? Well, because in graph Fourier transform, each and every time series is understood in a sense of how it is behaving with other time series. In spectral sequential cell, each time series is understood on its own. So as you can see, there is a 1D convolution, there is a discrete Fourier transform. So these are the operations which are performed on the time series on its own. So, so we have some representation of this time series inside a graph Fourier transform, and then we do a graph convolution. So what this achieves over here is trying to quantify this notion of how this particular time series is behaving in an ensemble of other time series. And then we do an inverse graph Fourier transform to counter basically this, and then we do a forecast, a standard forecasts. So this is a very high level idea of what's going inside. So we'll go deeper into each and every one of these small white blocks. So first of all, Fourier transform on graph. Okay, what does that mean? So if you think in a broad sense, all Fourier transform is express one thing, traditionally a time signal, in terms of other things. That is traditionally frequencies. That's what Fourier did in France, with some coefficients which signify how much of each frequency is present in the original signal, which are the LHS of this equation. So let's understand this equation. For example, f of x is our time series, is our graph, is our thing. Now what we are doing it is taking a dot product with this particular basis vector. And I'm calling it a basis vector because that's what it is. That's what linear algebra calls this. And then we are integrating over all possible x to find out how much of this frequency is present in this signal. So, and how would we get back our original function? Even if I cover this bottom half, how would you go about reversing that? So if for frequency equal to 100 hertz, I have this one amount of 1. I have the coefficient of Fourier is 1. So what I'll do, I'll add 1 of 100 hertz I'll have, let's say, 2 of 1000 hertz. So I'll add two frequency, 2 of 1000 hertz, and what I hope is when they are interfering with each other, the graph adds up in a way to regenerate our f of x back. So that's what also is happening in this particular equation. We have our coefficients which I very naively called 1 and 2, but these are the coefficients we are going to multiply with our frequencies, and then we are going to integrate over all frequencies in a hope to get our original signal back. So if we go a level higher and just think that linear in what is happening here is this: we are representing f of x in terms of some other basis vector. What initially was time t, we're going to express now in terms of frequencies, because that's just another representation, because that's just another basis, and then we can go back from that basis to time basis, because this is just linear algebra. So that's what this point says. They think linear algebra, that is expressing one vector here f of x as a sum of some other basis vectors. So okay, now we have some high level idea. So let's find what this so-called basis will be for our graph Fourier transform. So what my idea is that we have a graph, and for Fourier transform, what I'm going to do is, instead of representing it as nodes and edges, I'm going to represent in some other basis, some sort of basis, but some other basis. So now my next question will be, what is this basis? How will we ever find a basis for a graph? I mean, what does that even mean? So enter Laplacian for graphs. If any of you have some linear algebra idea, you'll know what Laplacian is. In at least in the Euclidean thing, in the continuous Laplacian sense. But what does Laplacian mean for graph? So this is just another way to represent graphs. This is also a graph counterpart for Laplacian in the Euclidean space. So for example, we have this graph. We have a degree matrix. What this degree matrix tells us is what is the degree of each and every node. So it will be a diagonal matrix. There will be no off diagonal elements. And the adjacency matrix tells us basically the edges. So wherever there is a 1, that means there is an edge between that row and the column of that one. So here it is node 1 and 2, and sure enough, there is an edge over there. So what degree matrix and the adjacency matrix play a part in Laplacian matrix is because Laplacian matrix is degree minus the adjacency matrix. That's what Laplacian matrix is. So as you can see, this is how the Laplacian matrix is formed. And why Laplacian? So why, what's so great about the Laplacian? Before that, let's just focus on this, that if a graph had what would Laplacian look in case of weighted graphs, or in our case. So if a graph has weights wij associated with the edges, then the Laplacian can incorporate such weights. So basically we have Laplacian as the degree minus w, but degree won't be degree in this case. It will just be the sum of all the weights. So if you go back a slide and look at a particular row, each and every row will add up to 1, because in a non-weighted graph, the degree will be equal to sum of all the edges incident on it. But in this case, instead of a degree, we're going to use just the sum of weights basically to make each and every row 0. So let's digress a little bit. Let's talk about the Laplacian. What the hell is a Laplacian? So in mathematics, the Laplace operator, or Laplacian, is a differential operator given by the divergence of the gradient of a scalar function on Euclidean space. Okay. So for example, if I have a function that is a function of, let's say, x1, x2, x3 up to some xn variables, we calculated this gradient. What a gradient tells us of this particular del f by del xi, that will be the gradient. And what gradient tells me is how this graph is at this particular x. How this graph, if I put a ball there, where will it roll? Where is this steep? Where is the slope of this graph? And the Laplacian is the gradient of this function. So in if I were in one dimension only, the Laplacian would mean something like a double derivative, a second derivative of this particular graph. So physically, what Laplacian tells us is how diffusion will occur in a room. For example, if I put a perfume bottle in one corner of the room, how that perfume flows to the other corner of the room. How far? How will it flow? It goes in the north direction, then the east and the west, and then somehow reaches the other corner of the room. But that's what Laplacian says. In other words, given a function, how smoothly information will flow from one point in space to another. That's what Laplacian tells me. For example, if I put a function in water, then Laplacian will tell me how at each point water flows from that graph, how smoothly that water is flowing on that graph. Basically, a second derivative counterpart in multi-dimensional space. So in graphs, Laplace tell a similar story. For example, if I put a potential on one node of an electrical circuit, how this potential difference propagates to the rest of the network. That's what Laplacian tells me. So for example, if I put a, let's take this right hand side of our slides. For example, if I put a potential at node 0 and so it's very obvious, like all of these potentials will flow equally to all of the other nodes. So that's what this is telling me. If I put a potential at node 0, at node 1, 2, 3, 4, they are equal. All of these potential differences will be equal. But on the other hand, if I put a potential at node 1, it's obvious that first of all it will flow to 0, and then from 0 it will go to 2, 3, 4, and 5. So that's what this is also telling me, that if I put a potential at node 1, first of all, it will flow to node 0 with some potential, and then to node 2, 3, 4, and 5 with equal potentials, which whatever is the number. In this case, the Laplacian, the darker is faster basically. So if you look at the first row, just forget the diagonal elements because the potential can flow from itself to itself. But what diagonal elements are is just a number. It's just a number that adds up. But the lower is faster. So when we put potential at node 0 for node 1, 2, 3, and 4, this is a very dark color, but the interesting thing to notice is that it's the same color. So for node 1, 2, and 3, and 4, and 5, that is the same speed. But if I put at node 1, you can see that node 1 and 0 have that same color, the darker color, but node 1 and 3, 4, 5, 6, whatever, they have a little lighter, because first of all, potential goes from node 1 to node 0, and then it flows from 0 to 2, 3, 4, and 5, and 6, and whatever. So that's what Laplacian tells us, that Laplacian is just a way to function, a way to model how smooth the particular graph is. So Laplacian in discrete sense, this is basically what Laplacian is. It's the discrete counterpart of the continuous Laplacian function. So what's so interesting about the graph Laplacian? This graph Laplacian is a symmetric matrix. So it has real eigenvalues and eigenvectors, and the latter forming an orthogonal basis. The GL is positively semi-definite because it's a symmetric matrix, and eigenvalues are non-negative because it's semi-definite. So the eigenvectors are nice functions defined on the graph. So basically, all of this entire discussion boils down to this, that the graph Laplacian has nice eigenvectors because they are orthogonal, sorry, they are orthogonal basis, and they are real and they are nice, so to speak. So a bulb pops in my head, and now the question is, what do we do with here? What do we do with these? So remember, we were chasing basis for Fourier transform to convert our graph into some other representation. The presence of these nice orthonormal eigenvector present a clear choice for our basis. Finally, we'll have the graph Fourier transform. So let G be the graph, vertices and edges, be a weighted graph. L be its corresponding graph Laplacian, and F, that is a V2R, is a function defined on the vertices of G. So F in our case will be the time series function. So for from every vertex, it's going to a real number. So in our graph, I drew something like this: 1, 2, 3, 4, 5, and each and every node was a time series. So this is what F means. For time t equal to 0, let's say these values are all 0. So function F will be this of vertices to a real valued 0, 0, 0, 0, 0. So that's what F is. Our time series is, that's what F is denoted by. So here the function F will be the value of our time series at a particular time. I've written that on the slide as well. So the graph Fourier transform F is defined as take an fi. Just remember the Fourier transform formula which was given earlier. This one. Take our f, multiply it with those basis vectors, and sum. Give them some. Give it a good old sum operation. So this is what is going on over here as well. We have our f of I for I into 1 to n for all nodes, and then we'll multiply it with our basis vectors. So our f of I, so this is the inner product between f and our basis vectors, and basis vector, this is one for one basis vector, and this is our value of our graph Fourier transform for this particular eigenvalue for that particular eigenvector. So again, u's are the eigenvectors of our Laplacian and lambdas are the eigenvalues of our Laplacian of the graph. So graph Fourier transform for one f for a particular eigenvalue. So from here we have moved from graph representation, graph domain to eigenvector, eigenvalue domain, basically Laplacian domain, spectral domain for the graph, so to speak. So spend a minute or two here to understand. So here UL is those bases or eigenvectors. So what we did, we multiplied our f with those bases and we gave him an integration for all particular points. And for each and every basis vector, we'll have a coefficient. So, and lambdas are the eigenvalues. As there are n eigenvalues, our GFT converts a vector of n dimensions to another n-dimensional vector. So, as there are n eigenvalues of our graph, we are assuming, well, let's say distinct eigenvalues. So, even if they are not distinct, if there are repeated eigenvalues, we can change this. We can have it for repeated in a sense like let's not focus on that. So, or n times